Let's study section 3.10, transmission and distribution. Well, the generation side of electrical power systems usually receive the most attention. Due to the shift towards the utility restructuring, along with the emergence of distributed generation systems, now the newest interest has been shifting into the transmission and the distribution side of the business. Figure 3.33 shows the relative capital expenditure on transmission and distribution over the time. As we can see from this figure, that in the past, before the 1970s, the capital expenditure between the generation and the transmission are almost the same. After 1970s, capital expenditure of generation is above the capital investment of the transmission and distribution. Now, after 1990s, the capital expenditure of generation start to decline, is below the expenditures of transmission and distribution. So which means the transmission and distribution capital expenditure continue to rise, and after 1990s, the capital expenditure of transmission and distribution has become the main business of the power system. The power system uses large capacity, long distance, high voltage transmission lines to transmit power to the main load center. The highest voltage level has developed from the original 161 kilowatt to the current 765 kilowatt. 765 kilowatt is the highest voltage level in the United States. But as we know that in China, we have developed the voltage transmission line with the voltage level over or at 1,000 kilowatt. Power is transmitted to distribution substation around the load by the highest voltage by high voltage distribution line. In the distribution substation, the voltage level is further reduced to the typical 4.16 kilowatt to 24.94 kilowatt, and the power is supplied to the users through the feeders. Figure 3.334 shows a simple distribution substation. Using a one-line diagram. The one-line diagram uses a single conductor on the diagram correspond to the three lines in a three-phase system. As we can see in these figures, this is we call the sub-transmission system. The voltage level is between 34.5 kilowatt to 138 kilowatt. And this is a sub-distribution substation. So this is called distribution substation transformer. This is the main component in the substation. We can also see that there are substation disconnect. There's a fuse to protect the transformer if there is a fault on the higher voltage end. These are lightning resistors. So when there's a lightning, this will be connected so that the lightning will not hit on the main component, cause damage on the component, but rather than the high current will directly go to the ground. They also have this bus breaker and the overcurrent relay. The overcurrent relay is to detect any fault on the lower voltage side and then will open up the breaker to protect to isolate the fault and protect the equipment. And this distribution substation transformer is using a delta WAN connection. And this voltage is between the 4.16 kilowatt to 24.94 kilowatt. There are a number of, we call the distribution feeders. This is called a feeder line. In each feeder, we have a feeder disconnect and the overcurrent relay. The overcurrent relay detects any fault along the line and then open up the disconnect to be able to disconnect the system, or isolate the fault. And this is called the voltage regulator. And the feeder breaker is mainly used to help to open up the circuits. Notice the combination of switches, circuit breakers, and fuses that protect the key component and which allow different segments of the system to be isolated, either for maintenance or during the emergency fault. Section 3.10.1, the National Transmission Grid. As we can see from the figure 3.35, the transmission network in the United States is organized around the three major power grids: the Eastern Interconnect, the Western Interconnect, and the Texas Interconnect. The transmission of the U.S. electric power is divided into three quite separate power grids, and further divided into 10 North American Electric Reliability Council regions. The ECAR, East Central Area Reliability Coordination, ERCOT, Electric Reliability Council of Texas, FERC, Florida Reliability Coordinating Council, MAC, Mid-Atlantic Area Council, MAP, Mid-Continent Area Power Pool, Maine, Mid-American Interconnected Network, NAP, Northeast Power Pool, Northeast Power Coordinating Council, SERC, Southeastern Electric Reliability Council, SPP, Southwest Power Pool, WSCC, Western System Coordinating Council. Well, almost all power in the United States is transmitted over three-phase AC transmission lines. There are circumstances in which high-voltage DC direct current lines have certain benefits. HVDC lines are especially useful for interconnecting the power grid in one part of the country to a grid in another area, since problems associated with exactly matching frequency, phase, and voltages are eliminated in using direct current lines. The control and interference simplicity of direct current DC makes HVDC links particularly well suited for connecting AC grid that operated with different frequencies. For example, in Japan, has two AC grid with two different frequencies. One is 50 Hz, another is 60 Hz. So HVDC is suitable to link two different frequency AC grid together. HVDC link require converters at both ends of the DC transmission line to rectify AC to DC and then to invert DC back to AC. The inverters at each end can operate either as a rectifier or as an inverter, which allows power flow in either direction. Figure 3.36 shows a simple one-line diagram of a DC link between AC systems. So this side is one AC system. This is another AC system. The first is through the transformer and using the rectifier to convert from AC to DC, and then using the inverter to convert DC back to AC, then through the transformer connected with the other AC system. HVDC line offer the most economic form of transmission over very long distance. The distance should be beyond 500 miles and above. For this longer distance, the actual cost of converters at each end can be more than offset by the reduction in transmission line and the tower losses. Section 3.10.2 Transmission line. The physical characteristics of transmission line depend very much on the voltage that they carry. Cables carrying higher voltage must be spaced further apart from each other and from the ground to prevent arcing from line to line, and high current levels require thicker conductors. Table 3.5 shows the common voltage used in the United States. For the transmission, they have the voltage level have 765, 500, 345, 230, and 161. Sub-transmission include 138, 115, 69, 46, and 34.5. Distribution. The voltage level can be 24.94, 22.86, 13.8, 13.2, 12.47, 8.32, 4.16. On the user end or the utilization end, the voltage is a 600 volt, 480 volt, 240 volt, 208 volt, and 120 volt. Figure 3.37 shows example of towers used for various representative transmission and sub-transmission voltages. The graph A shows the voltage, the transmission at the 500 voltage kilowatt, 500 kilowatt. This is a transmission tower. We can see this tower have pretty wide range and is 84 inches. And they also have the bottom end have the 48 inches. This can carry actually the two lines at the same time. This is one side. This is the other side. In fact, the line is not connect with the towers directly, but through this called it's carried through the connected over this line, carried through the conductor. Conductors is hung up on this point. This is also called ground wire, and this is the conductors. This tower is also can be used for the 500 kilowatt. The graph B shows for the three-phase lines for one tower for 230 kilowatt transmission lines. This is the pole, 230 kilowatt transmission pole. The space is used to prevent the arcing between the line to line. since all these lines are carried by very high voltages. And C shows the 69 kilowatt wood tower, and D shows the 48 kilowatt wood tower. These are the insulators, which is not conduct the electricity, and the transmission line will hang on through this point. Section 3.10, overhead transmission lines are usually uninsulated, strand aluminum or copper wire that often wrapped around a steel core to add strength. As we can see from figure 3.38, the inner is a steel strand, and outsider is an aluminum strand. The resistance of such cable is obviously important due to the I2R power losses in the wire, as they may carry hundreds of amps of current. So the higher of the resistor, the more power losses. Table 3.6 shows examples of cable resistance, diameters, and current carrying capacity. For example, the ACSR with the diameter of the 0.502 inches have the resistance 0.7603 ohm per mile, and the carrying amp capacity is 315 amps. We need to select the proper power the transmission line. So how to calculate or how to determine which type of conductor should be used? Let's say this example. Consider a 40-mile long three-phase 230 kilowatt. It's called a line-to-line voltage transmission system using a 0.02-inch diameter ACSR cable. The line supplies a three-phase, one-connected 100 megawatt load with a 0.9 power factor. Now let's find power losses in the transmission line and to calculate the efficiency. What saving would be achieved if power factor could be also corrected to 1.0? So there are two questions asked in this example. So the first, like to find out how to the power losses in the transmission line. Now first we need to, since we know they use a 0.05-inch diameter ACSR cable, so we need to find this cable's resistance. From the table 3.6, we know this cable has a 0.7603 ohm per mile resistance. Since they have a 40 miles long, so the total resistance is 30.41 ohm. The phase voltage from line to neutral, since it's one connected, so the phase voltage is equal to line voltage divided by the square root 3. Now the phase voltage is 132.79 kilovolt. As we know that the real power, the 100 megawatt real power delivered to the delivering three times through the three-phase system is equal to P is 3 multiplied 3 V phase, and I phase on an I line. Things is using one connected system. I line is equal to I phase. Multiply the power factor is equal to 100 and multiply the 10.6 volt. Therefore, we can calculate the total power transferred, and the line current and also is equal to the 100 multiplied 10.6 divided by 3 multiply 132.79 132,790 volt multiply the 0.9. Therefore, it's equal to the line current is equal to 278.9 amps. According to the table 3.6, the capability of this cable is a 315 amp. So the total, so this cable can sustain 278.9 amps. So this cable can be used to carry this line. The total line loss in three phase will be equal to 3 multiply I square R. Therefore, it's equal to 3 multiplied the 278.9 square multiplied the 30.41 ohm. That is equal to 7.097 megawatt. This is the total line loss over the three phases. Now, the overall efficiency of this transmission line is therefore equal to the power delivered divided by the input power, which is 100 divided by 100 plus 7.097, which is 93.37%. Therefore, there is a 6.67% losses in the transmission line. Now, if the power factor can be corrected to 1.0, therefore the line losses can be reduced to, the first we can calculate the line losses is 3 multiply 100 multiply the 10.6. Since this power factor has been changed from the 0.9 to the 1.0. Therefore, the total losses of this transmission line is 5.75. So using this one, we can recalculate the percentage of the transmission efficiency and the percentage of the transmission loss. We can see there's a 19% of reduction in the transmission losses. As wire heat up due to high ambient temperature and the self-heating associated with the internal losses, they not only expand and sag, which increase the likelihood of arcing or short out, but also their resistance also increases. So as we can see from this table, this resistance is based on at a 75 centigrade conductor temperature and with a 60 Hertz, and the ambiency of is the capacity of this transmission line is based on the 25-degree ambient and the 2 feet wind velocity. So, which means the resistance of the transmission line has effect on its own temperature, and also with the ambient temperature also affect the capacity of the transmission line. So when the temperature increases, the transmission line temperature increases, the transmission line or the wire, transmission wire and distribution wire will going to expand. Therefore, will cause sag. That the increase the arcing. The skin effect is the result of induced electromotive forces that opposite current flow by a greater amount at the center of the conductor than its edge. The result is that the current flows more easily through the outer edge of the conductor than in its center. The recent interest in DC lines is partly based on the lower resistance posed by the wires when carrying DC. Now, we complete the section 3.10.